welcome to this webinar on mastering leak prevention in extreme heat and chemicals. As my friend Rajesh has already given you an introduction of our company, and I am an applications engineer at Erith Group, and we'll directly begin with the presentation. So I'll give you a quick walkthrough for the agenda. We are going to be talking about high temperature applications. It's going to be VDH reactors, FCC units. We're going to talk about the challenges that we face in these extreme applications. We'll talk about the present solutions that are there and the continuing issues that are dealt with in these present solutions. Then we'll talk about the solutions that we have and how it's superior and how it has a great versatility. So beginning with this presentation, I would like to ask you guys a question. And I hope Rajesh can pull up the poll. My question here to you here is what is the challenging high temperature sealing application that you come across in your industries, in your installations? I've given a few options. You can select one of those. If it's not one of those, you can directly send it to me in chat. And uh, I just wanted to have an idea regarding your particular application. Okay. So most of the responses are for the petrochemical and gas processing, and there are a few for boiler and turbine applications. I suppose going ahead with this presentation, we will be dealing with your applications. So yeah, let's go ahead. So first off, we'll take the fluid catalytic cracking units, the FCC units. In a petrochemical refinery, the fluid catalytic cracking is one of the most important conversion processes used. It basically preheats a preheated long chain of feedstock is brought into contact with a very high temperature powder catalyst. This breaks the long chain of high boiling hydrocarbons into shorter chains, such as more valuable gasoline and other products. So this comes right under oil and gas industry, and talking about the fluid catalytic cracking unit itself. Under proper conditions, this catalytic cracking can produce shorter chain hydrocarbons, and it is divided into main three parts. The cracking unit itself is composed of three units. The main column, it's the reactor and the regenerator. Reactor is where the most of the high temperature reactions takes place, and even higher temperatures are generated in the regenerator, where the catalyst is regenerated. So this is a basic idea of what a fluid catalytic cracking unit is. So basically, under proper conditions, finely divided solids could be made to flow like liquids. Such small particles offer advantage in heat transfer and mass diffusion over large catalyst pellets. So this is why it's called a fluid catalytic cracking. In the cracking unit, it's an endothermic reaction. However, in the regeneration unit, it is a strong exothermic reaction. And this is the reason regenerators witness higher temperatures. as compared to other units. So due to the high temperature required for the catalyst to work in the FCC process, finding sealant material that can handle the temperature can be difficult. The modern FCC units are all continuous process units, which operate like 24 hours a day for as long as 3 to 5 years between scheduled shutdowns for routine maintenance. So a sealing material that can handle these high temperatures, the chemical attacks, as well as longer durations of working without failure is quite a challenge. So for this FCC units are generally used in the production of propylene through propylene dehydrogenation units. So propylene is second in importance to ethylene as a raw material for petrochemical manufacturing. The largest source of petrochemical propylene is that produced as a byproduct of ethylene manufacture. Ethylene plants that are charging liquid feedstock typically produce about 15% by weight of propylene and provide almost 70% of the propylene consumed by the petrochemical industries comes from this process. Uh, since crackers produce more ethylene than propylene, and its construction is tied to the demands for ethylene, so there is a need to create more channels for the production of propylene. One such channel is the FCC produced propylene. This helps in meeting with the increase in demand for propylene and bridge the gap in future. So there are many types of technologies for propylene dehydrogenation, and these are licensed by different companies. One of the major ones that we see is the Oleflex by Honeywell UOP, and the other is the Catofin, which is licensed by Loomis Technology. There are many other ones. There's KBR is there, based on the different types of configurations, and many other licensors are there. These are the major ones that we see around in operation. So basically, it has two parts. As I said, the reactor and the generator that are of main importance to us in this discussion. So talking about the regenerator, basically the regenerator operates at a temperature of about 715 degrees Celsius and a pressure of about 2 to 2.5 bars. So hence, since the regenerator operates at about 0.7 bars higher than the reactor, um, the regenerator and the reactor both have high temperatures. And talking about the regenerator, the combustion of coke that happens in the regenerator to reactivate the catalyst is exothermic reaction, and it produces a large amount of heat that is partially absorbed by the regenerated catalyst and provides the heat required for the vaporization of the feedstock and the endothermic reaction that takes place in the reactor. So a hot catalyst of about 715 degrees Celsius, leaving the regenerator. There are piping systems that connect all these units all throughout. And this catalyst flows into a catalyst withdrawal well. So there also it has to be contained in vessels, pressure vessels. Here also flue gases are allowed to escape. So that introduces another set of piping systems all throughout. So basically, we have an understanding that there are going to be connections through this piping system. There are going to be connections at these vents, at these flanged connections, at the boundaries of these different units. So we know that there are going to be joints, and these joints need to be sealed using a good sealing material. So going ahead, another high temperature application is the incineration that is used in most industries. So it's basically incineration is used for the thermal breakdown of effluents into non-polluting elements. So as to comply with the Environmental Protection Agency as well as different environmental agencies throughout the globe, every industry needs to uh, comply to their requirements. And for this, most industries have an incineration unit. So incineration can be of two types. There is conventional, that is high temperature incinerators, where the gases are heated to between 750 to 815 degrees Celsius and held at that temperature. That's called the holding temperature from 0.3 to 1 seconds generally. The other type of incinerators are the catalytic incinerators, where the decomposition is carried out based with the help of a metal catalyst. But however, the temperatures here are quite low as compared to the conventional conventional incinerators. So most incinerators that are operating at a higher temperatures than the ignition temperature of the effluent gases, which is the minimum temperature for an incinerator to work. The thermal destruction of these organic compounds occur at from 590 to 650 degrees Celsius, going up to about 980 to 1200 degrees Celsius. So as we are ensure that there's a complete destruction of organic compounds. uh, One of the there are multiple different high temperature applications that we come across, whether it be oil and gas industry or whether it be power generation. We have natural gas processing for the production of different organic compounds, hydrocarbons. We do have this desulphurization, which has high temperature as well as severe chemical service that we see in the industry. Apart from that, we have turbocharging and exhaust systems that have higher temperatures, and then there is heat transfer fluid sealing, which is a very high temperature as well as a critical application in terms of fire hazards. So apart from that, we have the power generation, the steam turbine, as well as different chemical processing units. So these are the few of the applications there for high temperature sealing that we come across in the industry. Going ahead, I'd like to ask you another question. For this severe service that you have just severe temperature and chemical service that you have come across, we have discussed now. What are the materials do you suppose that can handle the discussed high temperature applications? There are few of that we know of, and I've put those in the options. One is the mica, the second is the graphite, the third is the ceramic, and four is the vermiculite. So I would like to know which materials do you think, which material out of these that can best work in this kind of environment, and as well as is one of these the material that you guys utilize in your own industries, if so? So we have quite a lot of options for selections for the option of vermiculite, and as well as a few for graphite, and for mica too. So almost all of these materials have high temperature capabilities. Apart from these capabilities, that the materials themselves have some shortcomings. So we'll discuss each of these materials going ahead. So the past sealing gasket material have been asbestos, which has been banned throughout now. We have mica. Uh, one, uh, One of those is ceramic that we discussed, and graphite. So these gasket sealing material have been used throughout for high temperature applications, but there has been issues with each one of them. And going ahead, we can take a look at those. So basically, to 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 have an understanding of their performance under high temperatures, we have a test data. The testing conditions uh, that these sealing materials were used as gaskets in a 2-inch 150 pressure class flange. And the tests were performed based on the European 3535 standards. The leakage rates were measured, and basically the line was pressured at 580 pounds per square inch of a gauge pressure, and the temperature was set at ambient. The media used for this testing was nitrogen, and as we can see, the leakage rate as compared to the gasket stresses mm, that were used so as to stop the leakage. We can see that the graphite was the quickest to seal at about 8,000 psi. The leakage rates were reduced to zero when as compared to the mica material, where like up to around 16,000 psi, the leakage rates were considerably high. The mica did start sealing at 11,000 psi, but as compared to this to ceramic, ceramic did not seal throughout, even at higher 23,000 psi gasket stress. So the leakage was still uh, recorded, a high amount of leakage, in fact. So we can say mica and ceramic are great as thermal insulators, but poor at sealability. Even though ceramic is a very hard material, but and good as a thermal has good thermal properties, but they are very poor at sealing. So going ahead, we'll be looking at thermogravimetric analysis. So this is one of the analysis that we do so as to find the rate of change of mass of any material, any sealing material, based on uh, based on time when it is put in high temperature application. So the mass of the sample is measured over time as the temperature changes, and this oxidation of the material, which reduces its mass, which reduces the mass of the sealing material at high temperatures, as it is recorded. So now comparing the material that did seal in the previous that we have seen the test, graphite did seal nicely at around 8,000 psi. But looking at the oxidation resistance through the thermogravimetric analysis, we see that as the temperature increased over a period of time, after about 40 minutes, when the temperature had reached about 800 degrees Celsius, we saw an accelerated oxidation of the graphite. This mind you that this graphite was an inhibited graphite, which has an additive of phosphorus oxidation inhibitor. So the graphite that was supposed to hold at around 650 degrees Celsius. It did hold to about 700 degrees, 8 to 800 degrees Celsius at 40 minutes of time. But it again, going further at about 45 minutes, when the temperature had reached about 900 to 1000 degrees Celsius, there was a rapid mass loss. And due to this rapid mass loss, almost all of the graphite was oxidized, and the mass of the graphite sample was close to zero at the end of this entire test. So we can say that graphite is great at sealing, but then again, it's not good at temperatures above 450 degrees Celsius. So what we have seen throughout another type of application is to use mica along with graphite as a filler material in spiral wound gaskets. So this has been used and to a bit of success, but again, it is not ideal for higher temperature applications. So now that we have seen, we know a few of the qualities that are desired for these kind of applications. We know we require good sealability. We require oxidation resistance, and this oxidation resistance and sealability should accompany uh, thermocycling. The thermocycling should not affect these properties, apart from the usual chemical and chemical resistance that we require in a gasket, or probably dielectric property that is desired in a sealing solutions. So going ahead, we introduce you with a material called the Thermopure Style 4122. Thermopure is a proprietary gasketing material designed for use in high temperature sealing applications. The extreme temperature capability of proprietary material allows highest continuous temperatures of 1000 degrees Celsius, also combining with good reducing and oxidizing capability. So it is not attacked by oxygen as much. It is produced using an environmentally free, solvent-free process. Then Thermopure from Garlock is yet another innovative sealing solution that provides more than just temperature resistance. Talking about high temperature gasketing, compressed non-asbestos gaskets sealed to about 204 degrees Celsius. Extreme grades can go up to 343 degrees Celsius. We know graphite has been utilized for up to 450 degrees Celsius in oxidizing environments. If it is not, it's a non-oxidizing environment, it can go up to 650 degrees Celsius. But Thermopure is like a class apart from these. The Thermopure gaskets are designed for use in extreme temperature conditions beyond the functionality of traditional inhibited graphite filler materials. The Thermopure is able to withstand high temperatures, whether continuous or in thermal cycling conditions. They excel very well in oxidizing environments where graphite is not suitable due to its rapid weight loss through oxidation. So going ahead, we'll talk about the Thermopure Style 4122 and we'll talk about how it excels in all the desirable properties of high temperature gasketing material. So looking at the values and benefits of this gasket, the entire family of products is thermally stable up to 1800 degree Fahrenheit. That's about 1000 degrees Celsius. It is resistant to oxidation. It has low weight loss due to oxidation. It resists liquid degradation as opposed to some other materials such as vermiculite, as well as it is electrically insulating. It has good chemical compatibility and it can resist a broad range of chemicals. We can we can safely say that the environmental impact of this gaskets production is very low, and other advantages is for installations and disassembly. This type of gasket has a very nice easy release feature. Apart from the fire safety, it has passed API 6 FB fire tests successfully, and it is two of the models like the cam profile and the spiral wound gaskets are fire safe. So going ahead now, we'll compare the Thermopure with these materials that we had previously tested. So looking at the same testing conditions of a 2-inch 150 pressure class flange, where we used the gaskets and we used it at around 580 psi gauge pressure at ambient temperatures. The test media was nitrogen, and we can see the leakage rates that were seen compared to the ceramic. We still haven't seen any sort of sealing at those high temperatures. We have already compared the graphite and as well as mica. Now we'll compare, as you can see in the maroon, the graph, you can see that even at 2000 psi, the gasket had started sealing at around 8000 psi. It has greatly reduced leakage rates at about 11,000 psi. It has attained a complete sealing of the nitrogen, and as compared to mica and ceramic, it has a huge advantage. So the Thermopure spiral wound gaskets obtain a tighter seal at even at lower gasket stresses. So going ahead, comparing the Thermopure with other material like the graphite that we have previously seen in the same thermogravimetric analysis. We can see as the temperature increased over a period of time, at about 40 minute mark, the graphite had started an accelerated mass loss. However, Thermopure initially at about 20-minute mark, it lost a bit of a mass, negligible amount, like around 4% to 5% of the mass was lost. But even at 45 minutes mark, up to 50 minutes mark, to 60 minutes mark, 60-minute mark, where the temperatures had reached from 800 to 1000 degrees Celsius, where the graphite had completely lost its mass. Thermopure still had 95% of its mass intact, whereas the graphite had completely lost its mass. So laboratory testing demonstrates the long-term high temperature stability of thermopure material compared to graphite. Uh, okay, going ahead, now comparing the same thermogravimetric analysis with thermopure and vermiculite gaskets. So we can see over a period of time, we can see as the temperature rises, the vermiculite rapidly starts losing its mass at about 1000 degrees Celsius. Uh, the residual mass of the vermiculite is quite low as compared to thermopure material, and the vermiculite has lost 10% of its original weight, whereas thermopure has maintained 95% of its original weight. So thermopure's proprietary formulation resists oxidation and has improved weight loss property by almost 2 times when compared to other high temperature organic based gaskets such as graphite and vermiculite. One of the properties, the desirable properties is for a sealing material is to hold its properties even in thermal cycling. When we encounter thermal cycling, uh, basically the gaskets have a good sealing properties when the temperatures are high, but when it goes back to ambient temperatures, that's when the issues start to develop. So this is a thermocycling test that was performed at about 438 degrees Celsius or about 1000 Fahrenheit in a 2-inch 300 pressure class race phase flange. The media again was nitrogen, and the internal pressures were 2 bar. Uh, this assembly was torqued to 60 foot-pounds, and the gasket thickness that was utilized was 1.6 mm of the gasket thickness. So going ahead, we'll look at the data from this thermocycling test as compared to thermopure with vermiculite. We see that at the initial pore torques and the ambient temperatures, the leakage rate for thermopure was 25, and for vermiculite was almost 10 times higher. It was about 249 milliliters per hour. And after the first thermal cycle, the temperature increases and reaches 1000 Fahrenheit. At that point, thermopure has a little high leakage rate, whereas the vermiculite gasket has considerably reduced leakage. But once this temperature goes down back to ambient temperatures, just after the cool down, thermopure has a leakage rate of 152 ml per hour, whereas the vermiculite gasket has or effectively lost sealing and has 717 milliliters per hour of leakage rate. We then again we do another thermocycle where we go up to 1000 Fahrenheit of temperature. Here we can see comparable sealing properties as to the first thermocycle for both the thermopure as well as vermiculite. But going ahead back to the ambient temperatures, we see that thermopure has comparable properties as to the previous ambient temperature cycle, but vermiculite has an increased amount of leakage rate throughout the second cycle. So we can see that because of thermal cycling, vermiculite gasket has started increased leakage rates. Similarly, comparing thermopure cam profile gaskets and thermopure corrugated metal gaskets with vermiculite spiral wound gaskets. We see that ambient temperatures, this time the initial leakage was quite low for the cam profile and the corrugated metal gasket, which have employed thermopure. As compared to the vermiculite gasket, it has 1 ml per hour of leakage rate. Going through the first cycle, we have a highly increased leakage rate in terms of vermiculite. However, there is negligible change in the leakage rates for camphor and the corrugated metal gaskets. Then again we go down to ambient temperatures, and the leakage rates comes down considerably for the vermiculite. Um, and the thermopure employing gaskets have comparable rates. However, the camphor file has an increased leakage rate, but with the minuscule amount. Going for the second thermal cycle, again the temperatures have been raised, and we see again that the vermiculite spiral wound gasket has increased leakage rates. Coming back to after to the end of the second thermal cycle, coming back to the ambient temperatures, the values for the thermopure employing gaskets, the camphor pile as well as the corrugated metal gaskets, the data is comparable to the previous cycle, but for vermiculite gaskets, as the temperature rises, the leakage rates are increasing. Similarly, we do the thermocycle tests, this time in a 3-inch 300 pressure class flange at 25,000 psi. This this test is done between mica, ceramic, thermopure phased gaskets. So these are all spiral wound gaskets employing filler material as mica ceramic, and this thermopure as a filler material as well as the facing material for the gasket. So initially, mica had higher leakage rates, and for ceramic, if as the data shows 100, this was the limit for recording the data. So the leakage rates might be quite even higher than 100 cubic centimeters per minute. So as you can see, the leakage at 1,000 degree Fahrenheit, there are very minuscule amount of change in in the thermopure phased gaskets. Mica had quite a reduced leakage, whereas some ceramic is again at a very high in leakage rate. Comparing it with the cool down phase, the mica had like almost 100 cc's per minute of leakage due to as I said, that 100 cc per minute of leakage rate is quite high, and it would have been even higher if you could measure it. But it is Mica has effectively lost sealing at this point. This is just the second cool down. And going ahead for the second cycle of thermal heating, we see that there was increased uh, so there was a good sealing in terms of mica, but even after the cool down for the second cycle, again we have all lost sealing with mica and ceramic. And the only comparable data for thermopure phase gaskets sealing even at the higher temperatures as well as the ambient cool down phases is for thermopure phase gaskets. So this proves the superiority of thermopure employing gaskets even as the thermopure phased spiral wound gaskets. So now comparing the properties of vermiculite and the Garlock thermopure. This is a hydrophobic comparison testing that we have done, where after 40 minutes of water exposure, the vermiculite, since it expands due to exposure to water, we see that the filler material from this winding has started to gain volume, whereas the Garlock thermopure does not has any change. After 4.5 hours of water exposure, we can see the vermiculite degrade the entire winding, as well as on the right hand side, you can see the Garlock thermopure is not unaffected. Going ahead, after 7 hours of water exposure, we can see the vermiculite has completely disintegrated out of the winding, and Garlock's thermopure and did not see any change. So good hydrophobic capability means good exposure to liquid media, condensate, and a long shelf life. So as well as talking about the chemical resistance, the proprietary formulation of the thermopure is resistant to a broad range of chemicals like titanium tetrachloride, molten salts, and other heavy oxidizers, even at elevated temperatures. Talking about the physical and dielectric properties of thermopure, according to ASTM test results, according to ASTM F105, the properties for a 1/16th inch of a gasket are on your screen. As you can see, the temperatures of a continuous maximum of 1000 degrees Celsius is perfectly okay for the thermopure. The thermopure cut sheet gaskets can be used for about 500 psi gauge pressures. Depending on the type of gasket that you're using, the pressures can go up. For the corrugated metal gaskets, we can have 1000 psi, and for the cam profiles, these type of gaskets can match the flange ratings in terms of pressure. Talking about the electrical insulation, Thermopure style for 4122 FC is electrically insulating. Basically, it provides electrical insulation, thus reducing the possibility of corrosion between flanges made of dissimilar metals. It has talking about the compressibility and recovery. It has a compressibility of about 35 to 45%. And a very high recovery rate of 18%. And comparing the creep relaxation, it has a low creep relaxation of about 25%. So all in all, these properties make it a superior gasketed sealing element even at elevated temperatures. So I'd like to ask you, uh, this is a question more directly directed towards the installers and the riggers that actually have to handle those gaskets. Have you had safety issues while handling gaskets during installation, or like do you find it difficult to remove the gasket after exposure to high temperatures? It's a simple yes or no question. You can put in your response. I think you guys have this poll on your screen now. Okay, as I can see for the polls, almost all of the responses are that they have been handling issues while disassembly of this gasket and during installation safety issues and during installations. So these type of issues are generally due to the steel cores of high temperature gaskets. So generally, application traditional high temperature gaskets have steel cores in them, either punched or tanked inserts of steel SS stainless steels in them. However, the thermopure gasket has a fiber core and has no sharp edges. It is safe to handle. The patent pending fiber core has no sharp edges, makes the gasket safer to handle when compared to traditional high temperature gaskets with steel cores, and also has an added advantage of being an easier cutting gasket. Even in the field, these gaskets can simply be cut. and there's no issues. However, metal tank gaskets are quite difficult, and especially not recommended to cut, especially not recommended to for field cutting. Talking about the ease of removal, the common gasket filler materials may have an adverse effect during flange disassembly. The adverse effects can be the adherence of the gasket filler material on the flange surface and the difficulty of removing the adhered filler material without damaging the flange surfaces. So basically, easy release from flange is a requirement of high temperature gasket that does not stick to flanges, making removal of gaskets difficult. So here we have a 3-inch 150 pressure class stainless steel 3 SS316 flange that was bolted to the that was after the disassembly. We can see that we have uh, uh, the gasket that is on this blind flange. As you can see, it is easily removed with the help of acetone or any other material. The simply wipe gasket gets wiped off. This is the advantage of talc-based gaskets. So the gasket removes easily from the flanges and does not stick to the flanges, making removal of gaskets easy and quick. So going ahead, we talk about the high temperature capabilities of the thermopure gaskets. We can see the thermopure styles 4122 flex seal, that is a spiral wound gasket, and the thermopure style 4122 cam style, that is the cam profile gaskets, have successfully passed fire tests according to API standards. These are very stringent fire test standards that go through thermal cycling, as well as increased pressure tests after those cycles. The thermopure utilizing gaskets in terms of spiral mount gaskets as well as cam profile gaskets, they have successfully passed the American Petroleum Institute 6FB fire tests. So now talking about how the versatility of utilizing Thermopure style 4122 in your gasketing applications. So basically, the Thermopure family product offers a unique advantage over conventional high temperature sealing solution, as it can be used in multiple different types of gaskets. So there are multiple configurations for these gaskets that are there. We have the sheets and cut gaskets. Um, uh, uh, we have the cam profile gaskets, we have the corrugated metal gaskets, we have the spiral wound gaskets. Talking about the sheet cut gaskets, it is high, extremely high temperature capable with the oxidation resistance. It is safe to handle as well as easily removable from the flanges. The plus point here is that it has low creep and high recovery. Talking about the spiral wound gaskets, there are two types of spiral wound gaskets that can utilize Thermopure. One is simply as a winding material, and the other is the faced spiral wound gasket. Here you can see the as a winding filler material, the Thermopure has been used. And the traditional spiral wound gaskets with Thermopure filler material is commercially available in different types of available with commercially available materials that are used for spiral wound gaskets. It can be stainless steel, it can be Inconel, it can be duplex material. Any material that is commercially available can for spiral wound gaskets can have Thermopure as a filler material. And going ahead, we have the Thermopure material. Basically, the Thermopure facing material from it helps in adhering to the winding faces of the traditional spiral wound gasket. This improves the sealability up to 10% in standard applications and helps to maintain the seal in applications where gasket compression is limited. It also has the facing also helps the compressive load to remain on the gasket sealing surfaces during temperature and pressure cyclic events. Again, all commercially available materials can be used in the manufacture of the inner ring or outer rings, as well as the winding for these spiral wound gaskets. Now we talk about the corrugated metal gaskets. It accommodates a wide range of temperatures and it seals effectively even during thermal cycling. Again, it's chemical resistance resistant since only the metal surface comes in contact with the media. It has a long service life and accommodates high and low compressive stresses as well. Talking about the cam profile gaskets, the serrations on the cam profile gasket concentrate bolt load on small area for tight seals at lower stresses. So the solid metal core resists cold flow over compression and blowout. So this is the reason why cam profiles are generally used. The rigid core of this gasket provides exceptional stability even in large size and facilitates handling and installation. So under compression, the thermopure fills the seating surface imperfections to form a tight seal for metal to metal connections and seals under low stresses. Talking about the applications of in real life applications of the thermopure gaskets, we have the petroleum refinery application in their FCC units. So basically, this is a case where a major refinery located in China installed a new fluid catalytic cracking unit with a capacity of about 2,000 kilometric tons annual. As a result, about 2,000 metal gaskets, spiral wound metal gaskets were used. However, they have used the filler material as vermiculite. Um, when the refinery performed a routine steam purge prior to the commissioning of the new FCC unit, the vermiculite gaskets were found to have failed. The entire uh, unit has applied about 2,000 vermiculite filler material using metallic gaskets. So vermiculite based gaskets, even though commonly used in high temperature applications, they are susceptible to damage from moisture and water. As you can see, the operating conditions here were like a 3/4 of an inch up till to 12 inches of 300 pressure class flange connections. The temperatures here were 480 degrees up to 730 degrees Celsius. Hence, we understand that the filler material used was vermiculite. Um, Basically, due to the moisture damage, the entire 2,000 gaskets needed to be removed, and they were successfully replaced with thermopure filler material and facing spiral wound gaskets. And like they were these kind of issues that are dealt that we come across in terms of water damage is completely eliminated with the help of thermopure material. Again, going ahead, another case that we have here is from the petroleum refinery utilizing an FCC unit. Here, the temperatures were 690 degrees Celsius to 730 degrees Celsius. The challenges that they faced were due to high temperatures required for this catalyst to work was to find a sealing element that could actually handle such high temperatures. The media was high temperature fume and exhaust at a pressure of about 2 bar. This catalytic cracking unit had spiral wound gaskets having thermopure as a filler material with perfect results, and there was no sign of bolt loosening or leakage as previously was an issue at their unit. Again, we have a hydrogen cracker furnace where the temperatures about 800 degrees Celsius were recorded, and the application of the flange type application from 1 inch to 4 inch of 300 pressure class sizes. The problem here that they have was the lack of a gasket material that could withstand the process temperature requirements. Undoubtedly, the thermopure cam profile gaskets were good solutions, and they have been in operation without failures now. So we have chemical processing unit from Taiwan that again had a temperature of 800 degrees Celsius. They were previously using asbestos material. Since the asbestos material is now banned, the solution was to utilize thermopure style 4122 as a material for their gasketing purposes, and uh, this was another successful application. Talking about the catalytic dehydrogenation splitter from a unit in China, where they were utilizing the Oleflex technology from Honeywell for their catalytic cracking. The media here was water vapor, oxygen, carbon dioxide, hydrogen chloride, and as well as chlorine, with the temperatures of from 650 degrees Celsius up to 670 degrees Celsius at 0.5 bars of pressure. The thermopure works perfectly fine in these conditions, and we had a successful installation of thermopure gaskets in the catalytic dehydrogenation splitter. We have another successful application in terms of biogas gasification unit. Here, the media was oxygen, air, steam, as well as synthetic gas, all at elevated temperatures, with the highest temperature being 1100 degree Fahrenheit of temperature. The pressure was 10 bars, and the sizes required for the gaskets was from 2 inch leading up to 24 inches. Um, Here, the problem faced was the lack of gasket material that could withstand the process temperature requirements. And the solution for this were style 4122 sheet cut gaskets, as well as corrugated metal gaskets and cam profiles. These again have been in operation without failures. The other type of applications of these high temperature gaskets has been in the terms of turbocharging equipment and engine room exhaust services. So here the significance of this type of application is the toxic exhaust fumes that have that might leak out of the connections into the confined spaces of the engine room. This can become a serious gas hazard in health hazard. So the operating conditions here are almost similar, same, ranging from about 540 degrees Celsius or over to about 600 degrees Celsius. Uh, uh, Here the applications were for the exhaust manifolds of turbochargers, where the aramid gaskets could not perform at all at these elevated temperatures. So thermopure style was used. In terms of inability of the graphite gaskets to seal, having being oxidized at such temperatures, the gasket experienced mass loss and failed to seal properly, leaking toxic fumes inside the engine room. So it created a health hazard, and the solution would be to apply the thermopure style 4122 in place of these graphite gaskets, and this created a successful seal and eliminated the health hazard. The thermopure style has certifications from the American Bureau of Shipping, as well as from DNV certifications for maritime products. Uh, Apart from the API 6FB that we've already discussed, we do have these two certifications also. Um, Giving an overview of the thermopure values and benefits, we can say this is an extreme temperature capable gasket with extremely good oxidation resistance and improved weight loss characteristics over other high temperature solutions. The thermopure has hydrophobic properties which resist water, and uh, also it has electrical insulation, which reduces the possibility of corrosion between dissimilar metals. In terms of handling and disassembly of these gaskets, they are easily releasable from the flanges. They do not stick to the flanges, and they are safer to handle since there are no sharp edges from the metallic cores and prevalent metal gasket solutions. So the ideal applications that we have not discussed in detail in this presentation has been the chemical processing and marine and land-based exhaust system that we have already discussed. Apart from that, we have the pharmaceutical industry, the pulp and paper industry, the mineral and fertilizer processing that requires higher chemical resistance. Apart from process drying equipment, these are other ideal applications for thermopure gaskets in terms of high temperature applications. So with this, we have covered sealing solutions for extreme temperature and chemical applications in as brief a manner as possible. Thank you for joining in for this web-based seminar. If you have any questions, please feel free to ask them now, and I'll be happy to answer any questions. If there are any questions, you can put it through in question and answer segment, and I'll be happy to answer those. Okay, so we hope for a safe, effective, and economical operations of your installations and facilities. Thank you for joining in for this webinar. A recording of this webinar will be sent to you shortly. We hope to see you again soon in the next one. Thank you for joining in. Have a nice day.